So this is Incomplete Information VCG contracts for a common agency. My name is Tal, and this is joint work with Lavi, Elisheva, Shamash, and Inbal Talgam-Cohen. So we all know markets as a tool for the allocation of goods, but we can also consider markets as a tool for the allocation of effort. The theory that models the allocation of effort is the celebrated principal-agent model, where an agent acts on behalf of a principal. I want to take this one step further and consider a more general model, where one common agent acts on behalf of multiple principals. This is known as the common agency model, and this often comes up in social media, where an influencer as the agent works to promote several brands, in online labor markets, where a freelancer as the agent works for multiple customers, multiple principals, or on online advertising, where a marketing agency as the agent bids for the ad space on behalf of multiple advertisers, multiple principals. Now, a main challenge in this model is the agency problem. There are actions that generate good outcomes for the principals, but are costly for the agent, who acts in his own self-interest. Now, to align the interest of the principals with those of the agent, the principals monetarily compensate the agent with payments. The compensation scheme is called a contract, and it is designed to incentivize the agent to take a desirable action. The problem of designing such a contract has three key ingredients. First one is incomplete information of the agent's action, known as hidden action or moral hazard. It corresponds to the realistic scenario where the principal cannot directly observe the agent's choice of action, only its resulting outcome. For example, advertisers do not closely follow the marketing agency real-time bidding process, but they do observe measurable outcomes like clicks. The contract thus depends on the outcome, which serves as a noisy indicator of the agent's action. Second, we enforce two standard properties of contracts. First is limited liability. It means that payments flow from the principal to the agent and not vice versa. Equivalently, that payments from the principal to the agent are always non-negative. This is a form of risk averseness of the agent, and it captures the case where the principals, say the employers, have deep pockets and cannot monetarily punish the agent, the freelancer, who is of more limited means. And as for the principals, we enforce individual rationality. It means that each principal's expected utility, value minus payment to the agent, is non-negative. This guarantees each principal's participation. And throughout, we'll refer to limited liability as LL and to individual rationality as IR. The third ingredient is the challenge of coordinating multiple principles that intensifies both problems above. So this is a quote from a Wikipedia page on multiple principles. And basically, it says that more issues arise since now not only is there asymmetric information between the principals as a group and the agent whose action is hidden, there is also asymmetric information among principals themselves. Since each principal might have different privately known value for each outcome, their interests often diverge. So the classic literature on multiple principles has thoroughly explored one class of contracts, where each principal independently sets forth a payment scheme to the agent and then pays accordingly. We refer to these contracts as first price contracts, reminiscent to first price auctions where each bidder simply pays her bid. We show that first price can be very inefficient in terms of social welfare. And this is not surprising, since in this type of contract there is no coordination among principals, and it can cost the agent's choice of action to differ from what is in the joint principal's interest. Now, to be able to coordinate all principals, we consider more sophisticated contract formats. Specifically, we study what is called contractable contracts, in which the payment of one principal can depend on the contract submitted by the other principals. And our premise of this talk is that contractable contracts will enrich contract design for multiple principals, just as auctions beyond first price enrich auction design for multiple buyers. More than that, we'll see that the computational toolbox will be very instrumental in realizing this potential. So now I'm going to get into the following model. It formulates a game that allows us to consider more sophisticated contracts beyond first price. So what do we need for a model? We have an agent and we have multiple principals. The agent has a set of actions available to him, each one bears a cost, and stochastically results in an observable outcome. We assume that the probability for an outcome given an action is publicly known, so that the weights on those edges are publicly known. Then, as mentioned before, we assume that principals have different private values for different outcomes, and that this whole valuation profile is assumed to belong to a prescribed domain, referred to as the valuation domain. So this is the basic setting, and now we need to define what is a contract as a mathematical object. What we want from a contract is to generate payment schemes that incentivize the agent to take a desirable action, which we denote with A star V. We focus on the welfare, where the welfare of an action A is the sum of principal's expected value, given A, minus the cost that the agent bears for taking A. And A star V, the desirable action, will be the one that maximizes the welfare. So this is the socially efficient action. So a contract will be a mapping from the valuation profile into outcome-specific payments. It formally consists of n functions from the valuation domain and the outcome set to R. So all in all, the game proceeds as follows. First, since principals' valuations are privately known to every principal, all principals simultaneously give their reported values, referred to as their bids. A bid for an outcome is supposed to represent the principal's maximal willingness to pay for that outcome. So each principal submits a bid for each possible outcome, and then the bids are mapped according to the contract into outcome-specific payments. Based on that, the agent chooses an action, X star B, that maximizes his expected utility, payment minus cost, and finally an outcome is realized, and each principal pays the agent according to the contract's payment. And recall that we enforce two standard properties of contracts. First is limited liability. It means that payments from the principals to the agent are non-negative. And second is individual rationality. It means that each principal has non-negative expected utility, value minus payment, so that we can guarantee their participation. So, as mentioned before, the classic notion of a contract in common agency is what we refer to as first price contracts. And in these contracts, each principal independently sets forth a payment scheme to the agent. And in our model, it simply translates to having each principal paying her bid. So having each T equals to the corresponding B. First price contracts satisfy individual rationality, and they also satisfy limited liability. However, they suffer from severe inefficiency when considering social welfare. And we study the efficiency of first price contracts using the adherent measures of price of anarchy and price of stability. We show that the price of anarchy of first price contracts tend to zero when the number of when the number of principals tends to infinity. So informally, the worst equilibrium welfare in first price is infinitely worse than the optimal welfare. Second, we show that the price of stability of first price contracts tends to half when the number of actions tends to infinity. And again, simply put, it means that the best equilibrium welfare in first price is as 2 times worse than the optimal welfare. So to remedy the inefficiency of first price contracts, we suggest a new class of contract that is called IIVCG, which, similarly to their namesake, this is not surprising, as the renowned VCG mechanism guarantee welfare maximization. So a contract T is an IIVCG contract if the following two conditions hold. First is that the agent maximizes the reported social welfare. Second, the expected payment formula of principal L is of the following form: some function H that is independent of principal L's bid minus the welfare of others. So in this type of contracts, we have the same trick on payments as in the VCG mechanism. And by the same commonly known arguments, we can show that principals are induced to bid truthfully as a dominant strategy. So principal bids reflect their values, and since the agent maximizes the reported welfare, we get as a corollary that every IIVCG contract maximizes social welfare in a dominant strategy equilibrium. So this is a great starting point. First, dominant strategy truthfulness is a significant advantage of IIVCG over first price contracts. In first price contracts, it is unclear how principals even arrive at an equilibrium. And further, by being so close to the VCG mechanism, we can apply a well-known uniqueness result and show the uniqueness of the IIVCG class. So we show that every contract such that the agent maximizes welfare and the principals are induced to bid truthfully as a dominant strategy is an IIVCG contract. So this is all well and all good, but the definition of the IIVCG family raises some challenges that simply have no parallel in the mechanism design rule. First, the agent needs to be incentivized by the contract, by the payments, to maximize welfare. He's not a social designer, as in mechanism design, and we cannot force him to take the socially efficient action. And the second challenge is that we only have formula for the expected payments, but a contract must determine payments for every possible outcome realization. So the payments should be multidimensional. We tackle this challenge, these two challenges, by providing a complete characterization of outcome-specific payments that incentivize welfare maximization by the agent. And I won't get into the details of this lemma, but I will mention that it is useful since it exactly defines our design space, and in particular, it translates to linear constraints that are the cornerstone of the algorithmic construction we will shortly show. So we have a characterization of IIVCG contract, and we know they satisfy truthfulness and welfare maximization by the agent. But what about the other desiderata of individual rationality and limited liability? How do we choose payments from the above design space such that these two properties are satisfied? So actually, our results reveal that there is an inherent trade-off between individual rationality and limited liability. And while it is always possible to find an IIVCG contract that satisfies one of these properties, either limited liability or individual rationality, in some common agency settings, there is just no IIVCG, no truthful welfare maximizing contract that admits both properties. So combining limited liability and individual rationality, meaning protecting both sides of the market simultaneously, raises some surprising issues. So to overcome this impossibility result, we will change perspective, and instead of looking at IIVCG contracts which are individual rationality and limited liability simultaneously or not, we will look at common agency settings, and we try to characterize for which settings we do have an IIVCG contract that satisfies both properties. So just to make it clear, we have examples for settings in which there not exist an IIVCG contract that is both limited liability and individual rationality, and from this follows the impossibility result we mentioned earlier. And on the other hand, in the paper, we give examples for settings for which there exists an IIVCG contract that is both LL and IR. And in particular, we show that the settings where the price of anarchy and the price of stability were very low before, we do have such a contract. So what we do is to leverage our characterization and give an if and only if condition for the existence of an IR and LL contract that applies to common agency setting. Then we design two polynomial time algorithms. Algorithm 2 receives as an input a common agency setting and determines whether or not an IIVCG contract that is both LL and IR exists. And then, if such a contract exists, algorithm 1 implements it. So it receives principal's bid profile and stochastic resulted outcome as input and computes contractual payments on the fly for every principal. And the if and only if condition, just to be less mysterious, follows from this lemma. So fix the common agency setting and the contract T. If T satisfies limited liability and individual rationality, we have that for every bid profile, the total expected payments for the agent for taking them, for maximizing action, is sandwiched between some lower bound that comes from limited liability and some upper bound that comes from individual rationality, and we give both bounds in the paper. And from this, we work a bit to induce the condition that if every bid profile in the domain, for every bid profile in the domain, the lower bound is at most the upper bound, we have room to construct an IIVCG contract that is both limited liability and individual rationality, and vice versa. And I will mention that there is a conceptual difference between Algorithmic-IIVCG and classic contract formats given by a closed form formula function. However, every deterministic algorithm can be viewed as a function. And indeed, our algorithm yields a contract, a function. Further, the algorithmic basis of this approach may allow us the flexibility to protect both sides of the market with limited liability and individual rationality that may not exist when using a closed form formula function. So just to really quickly wrap up, we saw that the classic contract formats in common agency, first price contracts, are inefficient. We defined a family of socially efficient contracts, IIVCG, completely characterized them and showed their uniqueness. We revealed an inherent trade-off between limited liability and individual rationality and overcome it by introducing Algorithmic-IIVCG that gives two polynomial time algorithms. In the future, one can extend this model to multiple agents, ask about randomness, or think of contracts that guarantee both limited liability and individual rationality always for all settings, but approximately achieve the optimal welfare. So this is pretty much it. Thank you so much for listening.